In this video, we will be talking about logarithmic integration. So we've already talked about logarithmic differentiation, which is taking the derivative of log functions, but in this video, we're going to talk about integrating things that then give us a natural log function. And this little box here, the integration formula for natural log of u, will be very important for us. And it's important to remember that when we have this integration here, we do end up with an absolute value on the inside of the natural log. And that is because remember that the domain of natural log of x is 0 to infinity. So whatever is on the inside of the natural log has to be greater than 0. It has to be something that is positive. So we have that absolute value there to keep us from having anything negative on the inside of the natural log. So let's look at example 1. We have the integral of 2y over y squared minus 25 dy. We're integrating with respect to y here. We will be using u substitution. And after we go through the problem, I'll explain why we're doing it the way that we're doing it. So I'm going to start off and I'm going to let u equal y squared minus 25. And then we're going to take du in typical fashion. And when we take the derivative of y squared minus 25, the derivative of y squared is 2y. The derivative of 25 is 0. So we end up with 2y dy, which is perfect because 2y dy is exactly what is right there. And what we chose for u is exactly what is in the denominator. So now when we actually go to do our substitution, we have the integral of 1 over u du. Or you could have written it, we talked about this with that problem from the test, but this is the exact same thing as writing du divided by u. And then very conveniently here, we have the exact formula of what the integral of du over u is. And this is equal to natural log of the absolute value of u plus c. Then we're going to sub back in what u is and get natural log of the absolute value of y squared minus 25 plus c. And that is our final answer. So let's talk about how I knew what to choose for u. As I'm sure you've already experienced this with your exposure to integration, but as you're integrating functions, one thing that you will look for is if I choose u to be something that is in the denominator, will the derivative of that thing be in the numerator? If I choose u to be something that is in the denominator, will the derivative of that thing be in the numerator? So notice that what's circled in red in the denominator, y squared minus 25, we know how to take derivatives and we know how to do it pretty quickly now. The derivative of that is 2y, which is exactly what is in the numerator. So that is something that you need to be looking for as you continue to integrate functions. And remember, I told you that Calc 2 is all about integration. So we will still be talking about du over u when we get to Calc 2. Quick thing I want to mention. Yes, we could write the integral, and I'm going to write it like this, 1 over u du. Please, please, please realize that these two things are exactly the same. Okay, we talked about that during the test. So if I wrote it like this, which I will not be doing in the future, I could then rewrite the 1 over u as u to the negative 1 du. And then it may be tempting to use the integration formula that we know for when we have an exponent, that we increase our exponent by 1 and then divide by our new exponent. Let's talk really quickly about why that does not work for this one and why we have this specific rule. If we increase the exponent of negative 1 by 1, the new exponent on it will be 0. So we will have u to the 0, and then we would be dividing by 0. And this is a very big no-no, okay? So even if you're tempted when you see something like this, if you think, oh, I'll just rewrite it with a negative exponent, and then I'll use this rule. Even if you're tempted to do that, as soon as you add 1 to your exponent and get 0 and divide by your new exponent, as soon as you write this division by 0, something should be clicking in your head that, okay, no, I'm not doing this right because there's no way I'm supposed to be dividing by 0. Okay, so just a quick little blurb about that. And now let's look at example 2. So the first thing I will do in example 2 is I will pull I'll pull out the coefficient of 2 in front of the integral. So we have 2, the integral from 1 to 2 of natural log of x divided by x dx. So let's see. Earlier I had said if you see something in the denominator and the derivative of whatever is in the denominator is showing up in the numerator, you will be using this rule. That's exactly what we did in example 1. Let's see why that does not work for this case here. If I would have chosen u to be x, my du would be just a 1 dx. And that's problematic because we never captured the natural log that is sitting in the numerator of the integral. So this is not going to be one of those integrals where we're using this formula because that does not work. Choosing u to be in the denominator does not work here. So let's make a better choice for u here. What we learned in the previous lesson was that if we choose u to be natural log of x, the derivative of u, the derivative of natural log x, is 1 over x dx, which is good. And if you don't see why that's good yet, let's rewrite this integral to make it a little bit clearer. Instead of writing it as this fraction of natural log divided by x, I'm going to write it as natural log of x multiplied by 1 over x dx. And I hope you see that this and this are the exact same thing. And I can split it up like that. And you can imagine that I wrote the natural log of x with the denominator of 1, multiply straight across the top, multiply straight across the bottom. You will get exactly this same thing that we have there. Okay, so I rewrote it like that. So now that you can see that when I go in to do my substitution, this is u, natural log x. I will replace that with u. And this is du, 1 over x dx. I will put du right there. I will go ahead and bring down my integral and I'll bring down my 2, but I will be very careful with my limits because you cannot just put 1 and 2 on that integral since we have done a substitution. So I'm going to go off to the side here and I'm going to make a little table of x and u. I heard some conversations in the past few days, and I want to make sure we're very clear on how we find these new limits when we're doing a u substitution problem. We have the x values of 1 and 2. We plug those x values into u. We plug them into u. I heard some people talking about plugging them into whatever was on the inside of the integral. That is not what we do. We plug them into u. So when I plug 1 in, we have natural log of 1, and natural log of 1 is 0. And when we plug 2 in, we have natural log of 2. And natural log of 2, we will just leave that as natural log of 2. Please do not start putting these things in the calculator and getting decimal approximations for them. So our new lower limit, instead of 1, we now have 0, and instead of 2, we now have natural log of 2. Now let's integrate. Keep my coefficient of 2. I'll just write this down here. I'll keep my coefficient of 2 in the front. I'm actually going to integrate, so my integral sign is gone now. The integral of u, we increase the exponent by 1, so the new exponent is 2, and we divide by the new exponent. And then we will evaluate that from 0 to natural log of 2. The 2's cancel out, and we are just left with evaluating u squared from 0 to natural log of 2. You always plug in the upper limit first into the function. So we would have natural log of 2 all squared, and then we would be subtracting 0 squared. So we're just left with natural log of 2, which is all squared. In example 3, we are finding the area of a region bounded by a curve, the x-axis, and a vertical line of x. I'm going to just quickly pull up a graph of what that function looks like, the x over x squared plus 1. This is what the function looks like. Here is x equal to 3. X equal to 3 will be right there. That's the vertical line, x is equal to 3. And so what we're finding in this problem is what this area is here. Because we're bounded by the curve and we are also bounded by the x-axis. So I'm not going to go below the x-axis. So we're finding the area of that region shaded in blue. Let's go ahead and set our integral up. Notice that this region right here does start at the origin. You know, as I say that, I feel like I'm missing something in here. I feel like I'm also missing x is equal to 0. Please add that. And if you were given this problem, that would be given, because you do need to know that this integration is starting here at the y-axis. So we will be integrating from the lower limit of 0 to the upper limit of 3, and we will be integrating our function x over x squared plus 1 dx. So before we start talking about how we're actually going to integrate, look at this and think about what we talked about in example 1, what we talked about in example 2. Is this just going to be a typical U sub problem like what we had in example 2, where we did not have to use the new integration rule that we just learned at the beginning of this lesson? Or will we be using the integral of du over u rule, this rule? And the only time we will use this rule is if what you have in the denominator, its derivative shows up in the numerator. So let's look and see if that will work here. In the denominator, we have x squared plus 1. And there's nothing wrong, you all, with choosing a value of u, taking its derivative, and seeing that it does not work out. That is a part of the process of learning how to integrate. Let's see, if we choose u to be x squared plus 1, let's take du. Du is 2x dx. Now that's almost what we have, because we do have this x dx that's showing up here, but that's just this part. So we do not need that extra 2 that's in the front, so I'm going to divide both sides by 2, or multiply both sides by a half, same difference, which will give us that 1/2 du is equal to x dx. So now we are ready to start integrating, because we have u and we have what was left. Or we're ready to start substituting in, rather. So I have the integral. Again, I'm not writing my limits on it yet, because I do need to go and find what the new limits will be by plugging the old limits into what u is, not into what's in the inside of the integral, but into what u is. I'm going to go ahead and write what we have here. And I'll do this a few more times before I set up the substitution. I'm going to go back a second and just rewrite this, because we've had some conversations about this in class where I don't think it was very clear to everyone how we did the substitution. So I'm going to rewrite this as 1 over x squared plus 1, and then I will multiply by x dx. And again, I have not changed anything. It's the exact same thing. It's just a matter of, instead of writing the x in the numerator, I'm just writing the x off to the side. And we do know that it is really in the numerator. You can think of it as being over 1. So now I think it's a little bit clearer that this part right here is our 1/2 du. And clearly what we have in the denominator is just our u. So now let's actually start doing the substitution. Again, I'm leaving the limits blank for now until I actually come over here and do the change. But we have 1 over u in the denominator, and everything else that's left off to the side in orange is 1/2 du. So I'll write the du and I'll put the 1/2 out in front of the integral. Now let's actually go and find our new limits. Our old limits were 0 and 3. When we plug 0 into u, we get out 1. When we plug 3 into u, we get out 10. So our new lower limit is 1 and our new upper limit is 10. Keep in mind here that the way this integral is set up is the exact same thing as 1/2 the integral from 1 to 10 of du over u. Right? All I did was multiply the du by the 1 in the numerator and multiply the u by the 1 that we did not see in the denominator of the du. And I wrote it like that so you can see that it is exactly this rule up here that we will be using. So we have 1/2, I'm going to integrate now. The integral is the natural log of the absolute value of u, and then that needs to be evaluated from 1 to 10. So I'm going to keep the 1/2 out in front, and I'm going to open up parentheses and apply the fundamental theorem of calculus, which tells us to plug in the upper limit first, which is 10, to subtract, and then plug in the lower limit, which is 1. Natural log of 1 is 0. Any log with a 1 on the inside is going to be 0. So we are left with 1/2 natural log the absolute value of 10, and we don't need the absolute value because 10's absolute value is just 10. So we are left with 1/2 natural log of 10. I want to point something out because I know sometimes you all use computer algebra solvers, Mathway, whatever you want to call it, to solve problems. You may see this as natural log of the square root of 10. And those are the exact same thing. Because what you learned in 171, the power rule for logarithms, says that you can take the coefficient of a logarithm and send it to the exponent of what's on the inside of the logarithm. So 1/2 natural log 10 is the same thing as natural log 10 to the 1/2 power. And we know that exponents of 1/2 are the same thing as a square root. I'm not going to ask you to change your answers like that. I just want you to be aware that these two things are the same. Either answer would be okay with me. Let's look at this example that we have here. I would say, and I hope that at this point, especially after our last unit, which was all about integration and antiderivatives, thinking about U sub, that if you have something that is in parentheses with an exponent on it, most of the time that will be your U. Very rarely that will not be your U. So let's check and see if that will work for us here. If we let U equal x plus 1, then when we take the derivative of that, our du is just a simple dx. So the issue is choosing U as x plus 1 will take care of our denominator because we could just write it as a U squared. But the dx shows up there, that's not a problem. But what is a problem is specifically that x in the numerator. The 2 in the numerator is not an issue because we know we can just pull that out of the integral out in front. When you go through your substitution and you're still left with something that in the integral, like the x I circled in red, if the something that you are left with in the integral shows up in your expression for u, you will be doing a double substitution. So I'm going to be taking this equation for u and I'm going to be solving it to see that x is equal to u minus 1. So now I have everything covered in my integral and I'm ready to do my substitution. Before I substitute anything, I'm going to go ahead and pull that 2 out in front of the integral. So I'm left with x over x plus 1 squared dx. I'm also going to do the little rewrite thing so it's very clear how we're substituting in here. We have 1 over x plus 1 squared, and then we have an x, and we have a dx. So now let's go through our substitution. The 2 stays out in front. We have 1 over, instead of writing x plus 1 squared, I will be writing u squared. Instead of writing x, I will be writing u minus 1. And instead of writing du, I will be writing dx. Sorry, instead of writing dx, I will be writing du. There we go. So we've done our substitution. Now I'm going to undo what I did and kind of put this back together as, well, you know what? Let's not even think of it like that. Let's just go ahead and distribute this. Because I've had a few conversations with some of y'all. We do not integrate over products. In other words, what I mean by that is I would be very disappointed if I saw someone say, well, I'm going to take the integral of 1 over u squared du, and then I'm going to multiply that by the integral of u minus 1 du. Like integrate this over here and integrate that over here and multiply in between them. I know I'm going off on a tangent here. Tangent, calculus, get it? Anyways, I know I'm going off on a tangent here, but this is very important. And especially with us going into Calc 2, we do not need to be making these kind of rookie mistakes when it comes to integration. And even if you are inclined to integrate over a product like that, I would ask you, okay, how would you take the derivative of x times tan x? Let's say, how would you take the derivative of that? Because what you would not do is take the derivative of x, which is 1, and take the derivative of tangent, which is secant squared, and multiply them together. You would not do that. You would use the product rule. So the same way that we have to be very thoughtful when we're taking the derivative of products, we also have to be very thoughtful when we're taking an integral of products. So do not ever do this. That does not work. We can integrate over sums the same way we can take a derivative over sums. And we can integrate over differences the same way we can take a derivative over differences. But the same way that we do not differentiate over products or differentiate over quotients, we do not integrate over products and we do not integrate over quotients. Okay, tangent over. I'm going to do my distributing in here. So I am left with a 2 out in front. I'm going to take the 1 over u squared and multiply it by the u, which will leave me with a 1 over u. Just real quick, I did 1 over u squared times u. which is u over u squared. And then one of the u's cancels to give me 1 over u. And then I'm going to take the 1 over u squared and I'm going to multiply it by 1. So I'm left with a negative 1 rather, 1 over u squared. So we have this. We still have the du at the end. Now that we no longer have a product on the inside of the integral and we now have a difference on the inside of the integral, now we can break it up into two separate integrals. The 2 would be applied to both integrals. Keep that in mind. So I'm going to use a big bracket here. I'll take the integral of the first term, 1 over u du, and I will subtract the integral of the second term, 1 over u squared du. And then I'll close my bracket. I'm just going to do a little bit of rewriting so it's very clear what rules we will be using. I'm going to multiply the du straight to that numerator in that first integral, giving me a du over u. And then I'm going to rewrite the 1 over u squared as a u to the negative 2, giving me the integral of u to the negative 2 du. And now we are ready to integrate. The integral of du over u is natural log absolute value of u. The integral of u to the negative 2, increase your exponent by 1 to negative 1, divide by your new exponent, negative 1. I'll close parentheses and add my c on the outside. If you added your c on the inside, that doesn't matter. You would have to distribute the 2 to it eventually, but it's still going to be a c. It's still going to be a constant. And remember, the whole point about the constant is that it could be anything. So it doesn't matter if you add it on the inside or if you add it on the outside. I'm just going to clean this up a little bit before I go. I'm going to switch to parentheses because the brackets aren't necessary anymore. Before I actually go back in and sub back in what u was, these two negatives here will come together to give me a plus, and then the u to the negative 1 is just a 1 over u. And I still have my plus c. Now I'm going to zoom out a bit so we can see what u was originally. It's sitting right up here. It was x plus 1, and so I will be subbing back in u for the answer. So we have 2 multiplied by natural log of the absolute value of, instead of writing u, I'm going to write x plus 1. And then plus, instead of writing 1 over u, I'm going to write 1 over x plus 1. Close parentheses, and then I'll add c at the end. And that gives us our final answer. Okay, on to example 5. While I'm doing this, take a look at example 5 and think about how you would start that. This example is going to be a little bit different. Let's just walk through the motions and see why this example is going to be different. If we choose u, keep in mind everything I'm about to do right now is not going to work, but I want to make sure you understand why it does not work. If I choose u to be what's in the denominator, which we have done several times so far through these examples, then my du would be 2x plus, no, it would be just 2x dx, which is not good because there's all of this in the numerator. There's an x squared and an x and the 1. So I did not capture everything that I needed to capture there. If I would have chose u to be what was in the numerator, then my du would have been 2x plus 1, which is still not good because the denominator just had an x plus 1. I can't even attempt to do a double substitution because of that x right there. Right? Like I could grab the x squared plus 1, but solving for that would mean moving the x over, and so I haven't really completed my substitution. So instead, how we are going to start this problem is we are going to start by simplifying what is on the inside of our integral. We're going to start by simplifying our integrand using long division. Yes, polynomial long division. This is going back to 171. So I'm going to take x squared plus 1 and I'm going to divide it. No, wrong way around. I'm going to take x squared plus x plus 1 and I'm going to divide it by x squared plus 1. Polynomial long division is all about leading terms. I look at the leading term out here. It is x squared. I wonder, what do I multiply x squared by to get the leading term that's under the division symbol? I multiply x squared by 1 to get the leading term. Then I'm going to take that 1. I'm going to multiply it by x squared. I'm going to take that 1 and I'm going to multiply it by 1. And I'm very intentionally writing that 1 under the constant term of what's under there. And then we subtract all of the terms. Let's go through this. So this cancels. I just bring this x straight down, and the 1 minus the 1 simply cancel each other out. The process stops here because if I ask what do I multiply x squared by to get x, that answer is 1 over x. And we do not start writing rational terms when we are doing polynomial long division. Polynomial long division stops when the exponent of what's down here is smaller than the exponent of what you are dividing by. So when we went through this division, we got I'm going to write it like this. I'll write it all out. X squared plus x plus 1 divided by x squared plus 1 had a quotient of 1 and a remainder of x. And the remainder stays on top of the divisor, which was x squared plus 1. Okay, so that's what we got. So everything that's in this blue box, everything in our integrand, is the exact same thing as this. And so we will be replacing it. So we now have instead the integral of 1 plus x over x squared plus 1 dx. By the way, just a notational thing, you all, if you write two terms on the inside of an integral, you need to put parentheses around it. Without parentheses, that's not written correctly. We are integrating over a sum. We just had this conversation, and so I can break this up into into a sum of two integrals. The integral of 1 is easy. That's just x. The second integral is where we're going to have to be thoughtful here. Let's see what happens if we choose our denominator to be u. And by the way, you all, I'll just go ahead and say this. If what you have in the denominator, if that exponent is 1 greater than the exponent of what you have in the numerator, you will very likely be doing u sub, and you will very likely be using this rule up here. And I will explain why as we go through our actual substitution. So I will be choosing u to be x squared plus 1. And then my du will be 2x dx. We do not need the 2, so I will say that 1/2 du is x dx. I divided both sides by 2, multiplied both sides by 1/2. The reason that I made the comment about the exponents thing with the exponent of the degree of the denominator being 1 more than the degree of the numerator is because if you choose something with an exponent of 2, as soon as you differentiate to get du, the exponent will drop down to 1. So when the degree of the denominator is 1 more than the degree of the numerator, it is very likely that you will be using a du over u integration rule, which is exactly what we have here. So let's go through our substitution here. I'm not going to go through rewriting this one. Please feel free to do so if you need to. The x dx is 1/2 du. So when I set up my integral, I'll go ahead and stick my du at the end. So I'll go ahead and stick my du at the end, and I'll stick my 1/2 out in front. What we are left with is this, which is u. I don't know why I switched to purple. What we're left with is this, which is u, and it's in the denominator. So I'm going to stick it in the denominator. Or you could have wrote it like right here. I'm just going to leave it how I wrote it. I'm going to move all this stuff closer. And we know how to integrate du over u. It's what this whole lesson is about. So we have x plus 1/2. The rule for integrating du over u is you get natural log of the absolute value of u, and do not forget your plus c once you're done integrating. By the way, technically the plus c should have been up here too, since we had already integrated this term. As soon as you integrate an indefinite integral, you need to have a constant. Last thing I will do is replace u with what it was, which was x squared plus 1. I'll keep my plus c at the end. And that gives us our final answer. Let's look at example 6. The integral of tan x dx. We've seen a couple integrals, especially in this last unit, where we needed to use a Pythagorean identity to integrate it. I remember back when we were in 172, we talked a lot about, if you see a squared we talked a lot about if you see a squared trig function, you should be thinking of a Pythagorean identity. this tangent is not squared. We could integrate tangent squared with the knowledge that we already have. In fact, we've probably integrated it already. You change it to secant squared minus 1. But just tangent x, we have not integrated. So let's look at how we integrate tan x. And I think, in fact, you all, there's the rules down here, yeah, for the integrals of all the trig functions. So what is going on here? Hold on. Okay, that was, well, okay, I think I got that together. What I was trying to say is we already knew this rule. We already knew this rule, but we have not talked about integrating tangent, secant, cotangent, or cosecant, because all 4 of those integrals, as you can see, involve the natural log. So let's go look and see how we get our answer as the natural log, or the negative natural log of cosine x. We start by rewriting tangent x as sine x over cosine x, which it is. And now we have a fraction on the inside. And when we have a fraction and we're doing integrating, as we have learned in this lesson, it is a good idea to see if I choose u to be what is in the denominator, will I see its derivative in the numerator? And we will, because the derivative of cosine x is negative sine x, and we'll add a dx on the end of that. Now we don't have the negative showing up in our integral, so I'll just say that negative du is sine x dx. And now let's go through our substitution rather. I will be replacing the sine x, I don't like that pen. I'll be replacing the sine x dx with a negative du. So I'll go ahead and stick a du at the end of my integral, and I'll stick the negative out in front. We are left with a cosine x that is showing up in the denominator. So in the denominator, I will put u. So we are left with the integral of du over u. So we have negative natural log absolute value of u plus c. And u was cosine x. So we get negative natural log of absolute value cosine x plus c as our final answer there. Okay. So this whole next page is well, not the whole page. 2 of the problems on this next page say try it. I am not going to do example 7. I'm going to leave example 7 as some extra credit. I want you to use the same idea of what we did in example 6 to integrate cotangent x. So rewrite it using a quotient identity from 172. Pick your choice of u. Your du should be showing up in the numerator. And that should fall out pretty quickly. Example 8 and 9 are very similar. They show us how to integrate secant and how to integrate cosecant. I am going to do one of these, and I'm going to leave the other one also as extra credit. And I don't know why. I feel like people are more afraid of cosecant and cotangent. So that's the one that I'm going to do. And I'm going to leave example 8 as extra credit as well. But the good news is after we do example 9, you'll know exactly how to set up example 8. So we want to integrate cosecant x dx. That's what we want to figure out here. And we're told to use the fact that cosecant x dx, or rather that cosecant x, which is exactly what we have, is equal to this expression here, which it clearly is, because those fractions, I could just cancel that out, because this green piece right here is just 1. But I want to show you why we rewrite it like that in order to be able to do this integration. So I'm going to rewrite this as not just cosecant x, but I'm going to multiply it by this cosecant x plus cotangent x, and I will also be dividing by this cosecant x plus cotangent x. And then of course we'll be adding our dx at the end. So it is in rewriting it like this that we are actually able to do our integration. Now I'm going to distribute this cosecant x out to the numerator. So I have the integral of cosecant squared x plus cosecant x cotangent x. And that's all over cosecant x plus cotangent x dx. And if you're wondering why I did that, well, for one, remember, we do not integrate over products. So there's no way I can start setting up this integral unless I have a clear substitution, which we do not. There's no way I can start setting up this integral with that product in there. So now let's see if we can find a good choice for you. And I hope, even though I know some of y'all don't yet have all of the trig derivatives memorized, but that will change with time. I hope you know your trig derivative. And let's talk about that real quick. There is no possible way that you can become efficient at integrating if you do not know your derivative rules very, very well. Because the whole way that we do U substitution, which is a huge concept in integration, the only way that we do U substitution is by picking a good U. And we only pick a good U if the derivative of U shows up in the integral. And we would not know that if we do not know how to take the derivative of U. So it is of the utmost importance that we understand how to take derivatives and that we know in our brain the derivative of all 6 of the trig functions. If you have not yet memorized that, you need to memorize that. And I know we do open note things sometimes and things like that, but we don't always do that. And you need to know the derivative. I know sometimes I give y'all sheets or whatever. That's not always going to happen. You need to know how to take the derivative of all 6 trig functions. Okay, tangent over. Let's see what happens. And I say that because if I went on that rant, because if you know the derivative of your 6 trig functions, it should be very obvious that U should be cosecant x plus cotangent x. And if that's not obvious to you, let's see why by taking du. The derivative of cosecant x is negative cosecant x cotangent x. And the derivative of cotangent x is negative cosecant squared x, which looks very, very similar to what we have in the numerator. Just for some clarity, I'm just going to rewrite the order of these 2 terms. So I didn't do anything here, but just change the order that these terms were written in. They're both still negative, boom, boom. And so I just changed the order. So again, if you knew your trig derivatives, you knew that this would show up. And wow, that is almost exactly what we have in the numerator. The only difference is in the numerator, both of these are positive. And in our du, they're both negative. And so I'm going to change their sign by dividing du by -1, or multiplying both sides of that by -1. To see that a negative du would be equal to a positive cosecant squared x plus cosecant x cotangent x, which is exactly what we have in the numerator. And so now we're ready to start doing some substitution. Oh, y'all, I have not written my dx. So go back to all these du's and make sure you put a dx on the end of that. Okay. So everything that's right here is exactly what's written in green on the right-hand side of this. So I will be subbing in a negative du for that. And then everything that we have in the denominator, cosecant x plus cotangent x, in fact, I'll just circle that in red. All of this is exactly what we chose as u. So this is du. That's a funky looking u. Du divided by u. And we know now from this lesson that the integral of du divided by u is natural log of the absolute value of u plus c. And I just brought this negative down that was already there. And the last thing that we will do is replace u with what it was when it was written in terms of x to get natural log of the absolute value of cosecant x plus cotangent x with a plus c on the end. So I want you to use this as, and which is exactly what we wanted to get, by the way, y'all. I want you to use this as a guide to try example 8 for extra credit. And I want you to use example 6 as a guide to try example 7 for extra credit.